All right, guys, we are working on 1.4 transformations. I wanted you to look at this video before class. Hopefully it'll help us quicken the pace in class and work through that. So let's get to it. Transformations, we've been working on a Desmos activity that allows us to see the general movements here. And we want to think about this as like a vertical movement and a horizontal movement, and how that actually affects the way we transform our graphs. This also forces us to have a basic idea of what our graphs look like. So in this case, with our first example here, we're going to be transforming or looking at the absolute value function. Now, if you don't know what the absolute value function looks like, I would highly recommend using Desmos. And just to show you that, I'll actually go to Desmos. So in Desmos, we can actually use our function, and they will have us do y equals, but we have x, I'm sorry, the absolute value of x, and it's visually there. We have this stretch, this absolute value function. It's a positive v is a way that we can think about it. And then from there, secondly, what we can look at is what happens to our function whenever we subtract one from it. And because of our Desmos activity, we should have a decent idea of what's going to happen here, in the sense of if we took our absolute value function and then we just subtracted 1, that should incorporate a vertical movement for us, which it does. And vertically speaking, it just moves our point, our vertex, from 0, 0 down to 0, 1, or 0, -1, my apologies. The vertex is a key point to pay attention to. However, it's not the only point that we pay attention to. If I am looking at this function, every single part of my function is moving down by 1, every single one of them. I'm taking my function and then I'm subtracting 1 from all of it. So if you go to any point on this graph, hence this one at -1, 1, our output will now be -1, 0. It moved down 1. The y value decreased by 1. So the overarching has been removed. Okay, that's something that we'll do here, or when we're dealing with vertical movements, is the whole graph is moving down. The whole thing is. Okay, so our second function here, note the difference. We would call this outside because it is outside of the absolute value function. And for h of x, our function is the absolute value of x minus 3. Let's see what that looks like. Make that disappear. We have y equals the absolute value of x minus 3. And note, with the green here, we actually have a shift. But in this case, it is not a vertical shift, it is a horizontal shift. And unlike what you might think here, you may think, oh, I see -3, this is to the left by 3. But whenever we're inside of our function, it is a resetting of the origin. So in order to figure out where this moves, we actually set the entire inside of the function equal to 0. And so we get x is equal to 3. That tells me that my function is moving to the right by 3. That's important because visually we think -3 means left. But in our case, it means to the right by 3 because we are resetting the origin. It is moving to the right by 3, hence why our point is at 3, 0. And again, that should be true for all points. So again, if I took this point here and moved it to the right by 3, 1, 2, 3, it becomes this point on the green graph, which it does. The whole function has been shifted to the right by 3. So our main idea is going to build from this. We have vertical movements and we have horizontal movements, and we want to work from that. All right, so noting all that, let's move forward. We have vertical movements and we have horizontal movements. Again, inside of our function, would be a horizontal movement. Outside of our function, we think of it as vertical. I didn't draw these by hand. Desmos kind of took care of that, so we're fine there. Moving on, the example down here, we actually did this in the book. This was actually one of your homework questions, or something similar to it. So I'm not too worried about that. Ideally, the big things we want to pay attention to with f of x here is if we're graphing this graph, this function, we need to know, one, do we have any domain restrictions? And the answer is yes, we do have a domain restriction because we're dealing with a square root, meaning we cannot have a negative underneath our square root. So if I looked at the square root of 16 minus x squared, remember, this value cannot be negative. We need a non-negative value. So in order to solve for that, we say 16 minus x squared must be greater than or equal to 0, non-negative. And from here we can solve. So we can say 16, when I add the x squared to the other side, is less or is greater than or equal to x squared. Take the square root of both sides. Anytime you take a square root with an inequality, you have to set up a double inequality. You say 16 is greater than or equal to, the square root of 16 is greater than or equal to x, which is greater than or equal to negative square root of 16. Note, the sign stayed the same. We had to add the negative portion into it. So we have 4 is greater than or equal to x, which is greater than or equal to negative 4. So our values only pop up between negative 4 and 4. Negative 4, positive 4. So when our x value equals that, we can plug in. Now, if we were to graph this, again, you can pick out points. If I chose x as 0, what happens at f of 0 here? If we choose 0, well, we'll have the square root of 16 minus 0 squared, or the square root of 16, which is 4. So when I choose 0, my output is a 4. So I'm up here. Again, we're going to take a few steps ahead and just anticipate, where are my perfect squares at? I have the square root of 1 that I really like. I like the square root of 4. I like the square root of 9. I like the square root of 16. Well, we just handled 16, and I need to pick values between 16 and 0, or between our 4s, right? Where x is negative 4 and positive 4. So my next question would be, like, what would make underneath my square root equal to 9? What would make it equal to 4? What would make it equal to 1? And so we can kind of play around with that, but it might also be useful just to pick out numbers. What happens when we do plug in 1? What happens when we do plug in 2, 3, 4, and so on? We might not get pretty numbers, but I know to get the zeros, we have to plug in both 4 and negative 4. So we should have something to do with there. And you can plug these in. If we choose 1, for instance, what is f of 1? We get the square root of 16 minus 1 squared, or minus 1. So you get the square root of 15. Okay, that's not really a pretty value, but the square root of 15 is similar to 4. It's almost 4, so it's way on up here. If we plug in 2, we have the square root of 16 minus 4, right? Let me erase, let me get some space here. Oh, wrong thing. There's my erase. All right, so if we plug in 2, f of 2, we get the square root of 16 minus 2 squared, or minus 4, which is the square root of 12. Again, still between 3 and 4, so it's still way on up there. And it's slowly starting to come down, though, and what we'll probably see is this semicircle type of shape. And if you kept plugging in numbers, that's what you would get. Okay, onward from here. The idea is that we should be able to think of domain, we should be able to think of what this might look like, but we can always, always, always plug in points. Okay, examples here. So 1.4, we're going to do this example is number 14 on page 48. You actually have the homework problem for 13. Looks very similar to this, so knowing this is going to be important. In this case, we're going to use function notation. So you're going to be looking at this graph. This is not a graph that we typically have an equation for. I actually had to graph this using a piecewise function. So that's fine. We can still have all these pieces, but this blue graph is representative of f of x. Okay, so this blue is f of x. We want to take advantage of how is it shifting. How is this shifting? And so our goal is we have our function and we're subtracting one from our function. Okay, note that this is quite literally outside of our function. And outside addition, subtraction, multiplication, division, anything outside of that function is a vertical shift or vertical movement. Okay, so in our case, if we're subtracting one, that means we're taking our function, and after we plot it, we're moving the entire function down by one. The nice thing is you can actually go point by point. So I can look at each of these points right here, and we're going to pick the pretty points here. We could pick these ones in the middle, but I want to pick the nice ones because each of these are going to move down by one. Like literally this point will go down to one. So I went from a height of 4 down to a height of 3. I'm going from a height of 3 down to a height of 2. A height of 0, height of -1, -1 to -2. And that's the beauty of this, is that we can actually just connect the dots now. The whole function moved down by 1. It is a vertical shift. Anytime that we have addition or subtraction, it will be a shift. For b, note we are inside of the function. So since we are inside of the function, in order to understand which direction it is moving, we need to set the inside equal to 0. So x plus 1 equal to 0. When you solve, you get x is equal to -1, which tells me I'm moving left by 1. Now, visually speaking, whenever I see f of x plus 1 inside, it's the opposite of what is happening. So plus 1, in my head, you would think to the right one, but it means left one. And just like we did for example A, we can look at the exact points here, and we can follow them directly. It's going to move left by 1. Every single point moves left by 1. Every single point. Okay, and again, this is a function that you probably have never graphed before, but it is representative of that blue line, f of x, and we are shifting it. So again, the purple in this case is f of x plus 1 inside our function. All right, next two. When we look at c, very similar, right? It is inside the function, which tells me this is going to be a horizontal shift. Since it is inside the function, I want to set it equal to 0, which tells me that I would have x equals +1, which means I'm moving to the right by 1. So I'm going to take all those points, and we're going to shift them to the right by 1. And again, creates a really simple shift. I think the Desmos activity that you dealt with, Match My Parabola, really illustrated this. It uses vertex form, so you weren't using function notation, but you were seeing how it demonstrates itself with equations. All right, D here is a little different. We have an additional piece. I know I have inside of my function. Let's actually answer things that we know. We've dealt with an inner function shift. So this is a horizontal shift to the right by 2. Again, we get that because we set x minus 2 equal to 0, and we get x is equal to 2. However, we also have this negative out in front. So the question might be like, well, what does that mean? And you should have seen this before, but a negative out in front of your function means that you are reflecting. A negative with your variable or a negative in front of your function means a reflection. Okay, now, the illustration here, the emphasis that we've been putting is this negative inside or outside of the function? In our case, it is outside of the function. If it was inside, it would be within our f of x. Ours is not, so it is outside. Any outside operation is a vertical movement. So this is a vertical reflection, meaning that we are going to go from the top and reflect it downward, okay? Or we are reflecting over the x-axis. I hesitate to say that. That is literally what is happening. We are flipping over this x-axis, but because it's a vertical movement, in explaining it using the x-axis tends to confuse people. So I want to be able to reflect this vertically. Okay, that means that my y value is the only thing changing. Y value changes. So for instance, our top point here, which is at -2, +4, should move to -2, -4. So again, all I'm doing here is I'm reflecting that point. Okay, this is only if we had the vertical reflection. Note that this also has a shift to the right. We must do the shift first, but I'm just illustrating the vertical reflection here. So if, for instance, we had a vertical reflection with the second point we have, which is at 0, 3, it would reflect down to 0, -3, so on and so forth. Okay. However, we have to deal with both the horizontal shift to the right by 2 and the vertical reflection. Now, let's actually do this piece by piece. So I'm gonna label this point as, let's use this point as A. Where would point A move? Now, anytime you have multiple movements, multiple translations, you need to consider order of operations. Okay, the first thing that order of operations would tell me to do is inside the parentheses. So I actually need to move to the right first. So I'm going to move to the right by 1, 2. Now we are at this point. I need to consider the next operation, which in our case would be this reflection, the multiplying by -1. So this point, A, is currently sitting at 0, 4. It has shifted to the right. The reflection is going to move it down to 0, -4. So this is my new A. We'll call it A prime. So move to the right, and then it reflected downward. All right. Second point. Let's just call this one B. Again, it's going to move to the right by 2, and then reflect downward. So it's at 2, 3. So it will reflect down to 2, -3. The y value is the only thing that changes. We'll call that one B prime. Point C moves to the right by 2, reflects across the x-axis. However, it's on the x-axis, so it's right where it is. So that new point is C prime. And then our last point here, we'll call it D. Point D moves to the right by 2 and then reflects across the x-axis, so it goes up to D prime. All right, let's erase some of this. So now my points A to B, or A prime to B prime, B prime to C prime, and C prime to D prime. That is a shift to the right by 2 in a vertical reflection all in one. All right. Now, Example E. Example E has a negative inside of my function. Just as we did in the previous example, anytime I multiply by a negative, that is going to represent a reflection. And our reflection, since it is inside, means that it will be a horizontal reflection. The horizontal reflection means that we are going over the y-axis, going left to right. Okay, so that means, again, point-wise, I can just take each of these points. Now I'm going horizontally. That tells me my height is not changing. That means my x-coordinate should be the opposite. So if this coordinate is -2, +4, it will reflect to be +2, +4. Our second point is on the y-axis, so when it reflects, it's actually going to be right where it is. Our third point is at 1, 0. So again, the height does not change, so that will stay at 0, but the x-coordinate will change to -1, 0. And lastly, we have one at 3, -1. So the next point will reflect to -3, -1. And again, we have our coordinates, so we can connect them now. And that would be a horizontal reflection. We are inside the function, multiplied by a negative, a horizontal reflection. The last few examples consider what happens whenever we have multiplication incorporated. In our case, we still want to identify, is example F inside or outside of the function? It's 1/2 times our function. It's outside. Since it is outside, this means that we have a vertical movement. Vertical to us, it's not being added, it's not being subtracted, so it's not moving up, it's not moving down. However, this is going to be a vertical. Whenever you multiply a number, it's a vertical stretch or shrink. You might also hear this as a dilation. So vertical stretch or shrink. As we've seen, the rules for vertical is pretty straightforward. If it says +3, we're moving up 3. If it's -10, we're moving down 10. In our case here, we're multiplying by 1/2. Read it as is. That means that we are shrinking vertically by 1/2. So if we're considering, again, our point up here at -2, 4, the height is going to change. The vertical, the height, is going to change by 1/2. Well, it's at a height of 4, so 1/2 of 4 is 2. So the new output would be at -2, 2. The second point is at a height of 3. So 1/2 of 3 would be 1 1/2. So that'll be our next point. The third point is at 0. 1/2 of 0 is still 0, so it stays right there. And then our next point is at -1. Well, 1/2 of -1 is -1/2. So our new function should look identical, but as you can see, it's just been squeezed. And it is a smaller form of it. It shrunk. Okay, I am going to do G. I actually do not really care about the extra here. So just G here. Again, we are multiplying inside. It is not a shift to the right or left because it's not addition or subtraction. It is multiplication inside. So inside, which tells me that we have a horizontal movement. And in this case, again, it's being multiplied. So it's either going to be a stretch or a shrink. Now, earlier we set it equal to 0 inside. In this case, we're not going to set it equal to 0. But instead of a stretch by 2, it means horizontal movement means that it's happening twice as fast. So I can get this whole graph into half the amount of space. Not twice the amount of space, but I can essentially, a way to think about it is I can fit two of the graphs in one. So just like we deal with a stretch, this will also be opposite of what you think. It's horizontal. Vertical is as is. Horizontal is opposite of what you think. So anytime we have this coordinated here, we set it equal to 0, or with addition subtraction. With multiplication, it will still be equal to 1, because 1 is the identity, the multiplicative identity. So 2x is equal to 1, so x is equal to 1/2. That means horizontally, we should be able to do it in half the value. What does that mean visually? So my point here, again, is at -2, 4. With a vertical stretch or vertical shrink, it just halved or stretched vertically. In our case, our x value is being shrunk by half. So it's not going to move up or down, it's going to move inward. It's shrinking. So if it's at -2, half of -2 is -1. So it's going to move in. 0, half of 0 is 0, so it stays there. Our next point is at a value of 1, so half of 1 is 1/2. Note that we're moving horizontally. It's a shrink horizontally, so I'm moving inward towards the y-axis. Our next point is at 3, so it'll move inward to 1/2. Again, note the height has not changed here. All my y values are still at their same height. I'm just doing it in half the distance. Again, visually speaking, you're doing the opposite of what you see for horizontal. It's saying multiply by 2. Our intuition says it's growing by 2, but mathematically it is shrinking by 2. Okay, that should be a good example here. I'm going to post this. You should be able to see it. Secondly, I'm going to go ahead and work out the homework solutions as well. So you should be able to work through your homework. And you should also have examples and solutions of how to do all the homework pieces. I think this will be valuable for you. So check it out, and come to class with questions and ready to go into more problems.